Hello, my name is Hanne van der Aalt, and I'm here together with Tim van Est. So we're going to talk to you today about a new technology we have built in Fusion that is involving injection molding simulation. It gives you a bit of a peek behind the curtain of what we've been up to in the last couple of years, and who we are trying to address, and what problems we're trying to solve, and what the problems are we're not trying to solve. So again, my name is Hanne van der Aalt. I'm one of the product managers for the injection molding technology in Autodesk. I've been around the injection molding industry and the injection molding simulation industry for over 20 years now. I started in the Netherlands as an application engineer, then became part of QA, did the QA department for Moldflow in the early 2000s. I've been product manager since 2007. And like as a product manager, my responsibility is to basically just talk to customers, understand what their needs are, and help direct the development team in terms of what is the product we need to build, and what are the functionalities that we have to build in and how it should work. So basically giving direction and prioritization to the development team. So Tim, over to you.
Thanks, Hanno. As you said, my name is Tim van Est. So I have my background is in plastics. My career started, and I hope at some point will end in plastics. I was a customer of Autodesk and Moldflow software for more than 20 years before joining Autodesk. Here I do training and consulting specifically to Moldflow, although I also dabble a bit with the Fusion generative design. So today we're going to look at injection molding simulation in Fusion. We're going to do a little bit of just overview of injection molding for those who aren't aware of what it is or why we use that. We're going to talk a bit about the persona and the focus. Basically, who is this for? Who is this intended for? And we're going to look at the software. We get to actually see what is at this point now a preview available within Fusion software. So if we just take a moment to kind of step back and say, well, what is injection molding? It is the predominant process to make plastic parts in the industry today. And these parts could be anything from garbage cans you see here to parts in your car to, things that go in your phone to parts that get sent out into space, right? It is truly across all industries, and there's really so many uses for plastics available out there today. So just to be clear, injection molding is what we're focused on here. So it's not blow molding, it's not extrusion, it's not carbon fiber, composite tapes that are molded. So we just want to kind of keep that focus. There are other methods of producing plastic parts, but injection molding is what we were focusing on here. So I just want to start with the basics, right? We've got an injection molding machine here. And what we're going to do, we're going to start with the little plastic pellets. We're going to put them into the machine where they are going to be melted. Once they are, melted and completely liquid, in fact, a side note on that, when we melt plastic pellets, they actually expand slightly by volume. So once they are melted, we're going to then inject them into the mold. And then as the part solidifies, and I mentioned that they expand slightly while melting, they shrink slightly as you freeze them. But once they are in a frozen state, or a solid state, I should say, the part is then ejected, and we basically, repeat that for as many parts as you need. So I want to just talk through this one more time as we animate this. Again, as we're injecting the molten plastic into the tool, in there, it's going to solidify once it's cool enough. At that point, we're going to pack, which is sort of helping to deal with that shrinkage. The part ejects, and then we repeat. Again, just one more time here. Again, we're injecting the molten plastic into the tool. It cools down. At some point then, we were going to go to the compensation phase to pack a little more material in. Once it's full, it will cool down until it's completely frozen. The part is ejected, and we repeat this process. So with all manufacturing processes, there are advantages to them. And so with injection molding, there's a lot of energy cost that goes into producing the mold itself. But once that mold is created, we're able to produce parts very quickly. I would say the typical cycle time for injection molding parts is about a minute apart. And those parts come out very repeatably, just shot after shot after shot. And that can be a simple part, that can be highly complex parts. And that's just one of the beauties of injection molding. In the end, it produces very low cost for all of the complexity and quality that you can get out. The other thing that's really great about the plastics industry is the great number of different material properties that are available. And so when we produce parts, we're basically really honing in on what are the exact properties we need out of the specific material we're going to choose. And so that way we can sort of almost like custom make the material properties for each and every part that we're going to produce. So while there are definitely advantages with all processes, there are some problems too. So these are some of the things we want to look at is, what happens if we cannot completely fill the mold? Are there visual defects? Are there any problems dimensionally? And of course, structurally, will the part perform? So we want to look at that more, and this is what we want to see as we're looking at simulating this process, right? We want to know, will there be a problem to fill that molten material into the mold to produce a full part? If not, we call it a short shot because it's not complete. And it can be caused by a number of things, right? Is the material or is the part wall thickness just too thin? Is the flow length too long from where we inject the plastic to the end of the part? Is the material really stiff material, hard to push? There are other factors, but these are a few of the main ones that we end up dealing with. Surface defects or visual effects. Here are a couple mugs from my trip a few years back with the family to Harry Potter World. We had a great time, and of course, we ordered some butterbeer. And of course, being in the plastics industry, when we're done, I'm staring at these mugs and I'm like, wow, look at the one on the left. I mean, the surface of this is just not very consistent. It's just it's deep here, it's shallow here. It doesn't look overly good. And if we look at the handle over here, we see sort of these pit marks or what we would call a sink mark, right? And this ultimately is showing a not very good quality produced part. Now, if we look at the part on the right, on the other hand, we see very uniform in that surface display or the surface finish there. It looks so much cleaner and a higher quality part. It is interesting, in this handle, there is a small section that's not a sink mark. It's actually what we would call a void, where instead of the material sinking from the outside, it basically sort of created a sink on the inside or a void on the inside. And these are, for a butterbeer mug, who cares, right? I'm enjoying the butterbeer. I'm not worried about the looks of this. But on most parts that consumers will see, feel, touch, right? People, if they have a poor surface appearance, they're going to see that and assume your part is poor quality or potentially not even purchase that part. And then finally, dimensional problems, right? I mentioned that as the molten plastic cools, it shrinks just a little bit. And if we do things that are not very uniform throughout our part, we end up with non-uniform shrinkage, which basically creates what we call warpage, where our parts are not really the shape that we intended them to be. Some parts that might not be a big deal, but most parts there's an effect because with plastic parts, we design the features in, we design the function that we need. This example here would be a 5-gallon, paint lid. And if it doesn't really fit on top very well, if you accidentally knock the pail over, well, that's a bad day for your carpet because you're just, the paint's going to leak out because the lid wasn't in the shape we intended and which allowed a leak. The last thing I'll mention too is, some of those issues I've already talked about, as well as some other things actually have the potential to cause structural performance problems where the part just doesn't perform as it's intended to. Sometimes that's from things like a weld line where the flow front as it flows comes together. Sometimes those end up being very weak. Sometimes it has to do with the material properties or the fiberglass that's in the material and the orientation, so sort of the direction that it flowed as it filled. And these end up potentially having structural problems for your part that would cause them to fail prematurely. And this is something that is for sure on our radar. We're not exploring that within fusion injection molding at the moment, but that is definitely something we are looking to in the future.
Yeah, and I think actually another thing we have to talk about is the industry itself. It's like when you go from, let's say, a part design to something of an injection molding machine, there's many different people involved. In many cases, there are different companies involved with different skill sets. So a designer maybe designs the exterior of the part, but then hands it over to a supplier who maybe design the ribbing behind it, and then it goes to a tool maker who maybe designs the mold, and maybe that goes to a person that actually mills the mold itself, and then it goes to another company who's going to do the actual molding. This is a very disconnected workflow, and with very disconnected domain expertises, if you will. So they all are responsible for delivering a good quality final product, but the molder maybe not be able to actually create a good quality part, not because he is a bad molder, but maybe because there were design problems in the early beginnings that were overlooked, and because of disconnects in people not always working with the same data, or not reusing information that's been created before. There's a lot of inefficiency in the process of getting from a design to an actual plastic product. So to give you an example, for instance, like one of the things we see quite often is that a design gets created and maybe it's a design version 1 or 5 being sent over to somebody that runs some injection molding simulations on it. The injection molding simulation guy thinks like, great, this is work, this is great. Gives a thumbs up to the designer, but the designer may have moved on to design version 10 by this time, and that can maybe get sent to a mold designer. Mold gets created, and that gets basically molded. But that part now may be completely different from the initial design that was evaluated by the injection molding simulation expert. So, and we see this kind of disconnects quite often in the industry. And if everybody would be working off the same data and be aware of what's been done before and be able to consume and contribute to that, that'd be really, really a big benefit for the industry itself. So next slide, please. So one of the things why I'm actually personally really interested in building technology on top of Fusion is that Fusion is basically has a mission to connect the design world to the manufacturing world, the make world, if you will. And one of the big advantages of this this platform is that once a design is created, it can be sent over to somebody that does a simulation on it. The simulation can be run, and the design can actually continue to work and be updated. And once that update actually gets submitted, you don't actually have to start the whole simulation from the ground up. You can actually start with just rerunning the analysis with an updated model, and so there's a lot of more efficiency in this place. And down the line, we hope to also be able to like take information that the mold flow or the injection molding simulation expert created in terms of, let's say, process that can be transferred to somebody running a molding process, and take the molding process that the injection molding simulation expert run as a starting point for setting up a mold. So data gets reused and not lost or has to be recreated. And there are people along the entire chain that can be contributing to this data and also consuming data to it. So I think there's a lot of efficiency that can come with with working on this type of platform. So next slide, please.
So Hanno, I have a question for you.
Go for
So
it.
I've been a Moldflow user for years and years. Is injection molding simulation in Fusion intended for me, or who is this really intended for?
So that's a really good question, Tim. So so you in our view of the world, like you are a simulation expert, you have spent your entire professional life in injection molding, right? So for and Moldflow is the tool you use on a day-to-day basis. This is the tool that you've grown up with, and for the foreseeable future, that actually still going to be the right tool. With the technology we put into injection and molding in Fusion, we're actually trying to address a different persona that's much more of a generalist, let's say a mechanical engineer that's probably spends more time doing structural engineering work. Somebody has to do a lot of communication with the designer, maybe spend some time negotiating with a tool maker, does some project management, but is not a plastics or injection molding expert by any stretch, has no ambition to be that. But he has to like make some informed decision on, is this design even feasible for manufacturing in injection molding? And building some confidence and having a way to sort of start a good discussion with a tool maker on exploring options and, let's say, where to put an injection location. So this is a different persona. So to answer your question directly, Tim, you as a mold expert will not have all the tools that you today in the technology preview we have today in Fusion. We will intend to build towards that, but not today. So like you said, we have built our, like as a Moldflow product community, we've always addressed our injection molding simulation analyst, specialist. For the foreseeable future, that actually still going to be the right tool for this. So like what we're trying to do with the Fusion injection molding technology, we're trying to address a different persona that can work in parallel or in collaboration with the injection molding expert. So imagine that I think when we talk to our users, we typically see quite a bit of time being spent on very trivial issues like where is the welding going to be, and like things that are really not that challenging, that shouldn't take the attention maybe of the expert. An expert should actually probably be spending more time on things like warpage that are really just much more meatier problems to solve. And if, let's say, an engineer can take care of a lot of the trivial work up front, and actually get to a point where there's confidence that this thing can be injection molded, then it can be handed over to an injection molding specialist or a mold designer who can figure out how to manufacture this thing efficiently. So if you have confidence that the design is okay to be manufactured, then the specialist can actually look at a different problem. How do we actually create an efficiently running mold that is going to do the job well? Next slide. So to take a step back again, so when we talk about an engineer persona, a generalist engineer, like I said, we have got a bit of a profile for this person, and this person actually will get involved in a lot of sort of technical or semi-technical discussions and we'll get involved in material choice and maybe evaluate some gate locations, but nothing super deep in sort of the weeds of injection molding. You will look at things like structural integrity of the part. So if this thing is molded, we'll actually be able to perform the job that it's intended to do. Also get into, because he works very closely with the designers, we expect this person to also have need to answer some questions around position of weld lines and defects like sink marks on the parts, so whether or not they exist and what to do about them. So and like I said, this person we expect this person to be involved in sort of sitting between the designer as well as the tool maker and have a lot of interaction with this side of the industry as well. So Tim, maybe this is a good point just to go into the software and just like see what it does today.
Sounds good, Anno. Excellent. So let's see. I read this file in directly just a minute ago here. So let's take a look. If I want to look at the new injection molding and infusion, we're going to come over here to design, and we're going to change over to our simulation workspace here. So here we do have, again, it shows preview at the very bottom there for our plastic injection molding simulation.
It's going to read in.
Read in. One of the first things I notice when this comes up, it says target body, which sort of makes sense because I don't want to simulate this entire thing. Not all of this is going to be injection molded. So I am just going to select one of the parts here and click OK. And that's pretty cool because it actually got rid of everything else for me to just show that I'm focused on just this part.
So Tim, is actually worth pointing out that the technology preview for now is a single part only analysis. So yes, you can simulate multiple components in the entire assembly, but they would be separate studies, if you will. So.
Excellent. So I see my part here, and I see my setup summary. So target body I see is on top, and I already selected that. Material. So here I can, right from here, it looks like I can select a material. And so this database, when I look at this, I see a whole lot of generic materials. And so if I know it's going to be an ABS, I could select this. But are there other materials just than generic in there?
Yeah, so if you look at the top, like so all results, there's almost 11 or more than 11,000 materials in this database. This is effectively the full database that runs behind Moldflow. That's characterized for injection molding simulation. So not only the mechanical properties for the particular materials, but also like the rheological, the viscosity behavior, how understanding how these plastics solidify and all that stuff that you need for injection molding simulation. And it's a big database with many different material suppliers, different many different grades, different families, and there's different ways to actually search this the database through either if you go with to say ABS on the top like in the search bar, yeah, it's going to give you a couple of suggestions what you might be searching for. You want to search for things with ABS in the name, ABS as a family trade name, or as a family itself. So, and if you know like what you do now, basically create the entire list of ABS materials. So there's different ways to search for the database, but it's like it's a topic on its own.
Excellent. Okay, so we'll pick a generic ABS for now. Next is the injection locations. So again, if you're not familiar with injection molding, the injection location is where we entering the molten material into this part in order to fill this out. So it looks like there is already one here, even though I have not set one yet. If I rotate the part around, I see this cone back here that's sort of just highlighting that this is somewhere to start. So it's interesting because I don't know that, again, after, you know, lots of years in the industry, I would exactly put the gate there. But I also sort of like that it just put one there right away, just to give me a feel, right? Even if I don't know where I'm going to put the gate, at least I could start with that to see overall, boy, is my part going to fill? And if I do know a little bit better, I of course could take this and I could move this somewhere else on the part, or I could add a second or a third injection location if I so desire. So, but I do like it just starts out with something because I could, again, if I don't know better, well, let's just see what happens from here. Next up here, I see things that I would consider to be process settings, right? Injection time, melt temp, mold temp. Is this something that I would often change, or are these default settings pretty good here?
So these are default settings for the material that you're using. So if you were to say pick a different material family, for instance, like you could instead change your generic ABS to a polystyrene, we'd be changing the melt temperature and the mold surface temperature to a different value, because that's sort of the recommendations for these this particular material at that point. The automatic injection time is another thing. Is like we don't expect most users, even like experienced multiple users, to have a really great sense for what the best injection time is going to be. So we have some algorithm running in the back to take care of that for you. So we're trying to make the setup as intuitive and easy as possible for you to get to a simulation. So if you look at the top bar toolbar next to the solve button there's a checkbox, a pre-check, and you already see that we have, even since the beginning, we basically put everything in place for you to actually start running an analysis immediately. So we picked a default material for you, which may not be the material that you're using, but if you, in many cases, we don't even know exactly what material is you're going to use, or where the injection point is going to be. But we're trying to get you to a point where you can already discover some limitations with the design that might be occurring in the design that do not require things to be 100% accurate at this point.
Nice.
And like I said, so, like you said, when you do know better, you have a better injection location where you know what material you're going to be using, you can actually make those changes pretty easily.
Cool.
But so the next thing,
yeah, I say the next thing I see here is says aesthetic faces, and it says 0. So in this case, I do know that there is going to be, you know, some surface area here that people will see when they're using this. So I see I can select that. What does that really get for me? Because I'm not changing anything here. I'm just selecting those.
Yeah. So that's a really good question. So this is actually one of the things we're trying to do with injection molding in Fusion, is that we're trying to create more, allow you to set more information into the system that we can help, that is going to be helpful for us to direct you in the right direction. So if we know that there's certain aesthetic faces on this particular part where visual appearance is important for you, there's 2 things we actually do with this at the moment. One is in the injection point. If you specify injection point location on an area that you designate as an aesthetic defect, we're going to highlight that for you. So if you move that injection point now, to something on the aesthetic face, and say apply it. Okay. So now the checkbox in the top, in the pre-check, now is saying, giving you a warning, because now you put a injection point on an aesthetic face, and it always leaves a visual mark. So now you have either a choice to either unselect a particular face, like, okay, I'm gonna allow the injection point on that particular face because that particular area may not be super important. I'm gonna put a sticker on this, or you basically move the injection location to an area that actually is going to be of less visual appearance, like there, for instance. Cool. So
very good. So at this point, I can hit solve, right? In fact, I could have hit solve right away, but here I've modified a few things. Correct. And we could hit solve. So, okay. So to save time during this presentation, I have already solved this. So let's hop over to one that has some results. Okay, so now that we've jumped into the model that's got the results, I just clicked on results, and here we come up. To start with, it just shows up with some results, and it's got a few different messages here on the left, saying, you know, with this study settings, the part will not fill completely, result in a short shot, and use the guidance below to address the problem. So here it's saying, you know, some areas won't fill at all. So if we turn this around, oh yeah, here we see this. And if I look carefully here, I see this rib is actually awfully thin, thinner than all the others. So it's saying that won't even fill. You know, some of this is unlikely to fill. A portion is no problem. And a big chunk is we can fill that. But I do like here it's saying next step, short shots. It's got some recommendations, things we can look at. And here, oh, it's even got the links, right? So things we could do to reduce the pressure required. I could edit an injection location. I could add a new one. And if I click this, it'll take me directly to there. Doesn't stop just there though. It kind of says we could, you know, change the thickness of my part. That's definitely probably the largest factor as far as parts being able to fill in the amount of pressure required to fill them is the wall thickness, or we could change it to a material that flows easier. So I like that it's got all of these descriptions of, hey, here's things that we think are going to be a problem. Here are possible solutions that you can consider.
And these are actually the recommendations that an injection molding expert actually would be going for first. If they see a problem like a short or like a problems filling occurring, what do? Let's move the injection location to a different place, maybe make some design changes to the part. And all those recommendations are part of that, the feedback we're providing to you. So not only show you the problems that are occurring, but also give you suggestions what to do about it. So nicely tied together. And actually, one of the things that's worth pointing out is like in fusion injection molding, we have a guided view area that answers 3 basic questions for the designer. Like, and we talked about these 3 things earlier in the presentation. Where will the part fill? Will it have fitting issues? Yes or no? Will it have visual defects? Will it have things that are appearing on a part that are of cosmetic concern, as well as like, will my part have massive warpage or like have some deformation issues? And we'll go through this in the next right now over here. So maybe they start with the visual defects. Yes.
So here I see a message saying 4 faces will have sync lines. Oh, and it even calls out the 19 of these faces will be, or 19 of the weld lines will be on aesthetic faces. So again, now I see why we were calling those out earlier to sort of show that. In fact, I've noticed this too. If I just put my mouse over that, I can kind of see which are those surfaces that will have some visual defects. And with that, which ones aren't, right? Which ones are green from a visual standpoint that are the aesthetic faces. Those are good to go. So if I need to focus somewhere on what or how to fix things, this is going to give me a great guide towards, hey, you better explore looking at this surface and what's happening there. So very cool.
Tim,
And
actually
then
on the toolbar, like on the right hand side, like you actually have a tolerance that you can manipulate. So if you in a company have maybe a maximum allowable depth for a sink mark, we made an assumption what it actually is. But if you have a let's say your own guidelines in the company for what's a maximum allowable sink mark, you can actually make the threshold value for what's allowable or not actually visible.
I like that. So again, we have the next steps here, things we can do to reduce it, different just suggestions on, hey, if this is going to be an actual problem for you, these are the things that you should look at to try to fix that problem. So if we go to the warpage tab here, will my part warp? Again, this is sort of just highlighting based on the default value here of the tolerance of what is excessive warp. But you just talked about this. If we need, we can shift this tolerance. Maybe the tolerance is, no more than 1 millimeter of movement. Well, now we can see how much of the part's not going to fall within that. And conversely, what if it's 1.5? What does that mean? Is it, if it's just this, what does that mean to me? I can then make a good decision. Do I believe that might be okay if it's outside of tolerance, or there's no way? And again, we've got sort of these guides here to kind of say, hey, in order to reduce this, you might consider looking at these specific things to change this.
There's actually 2 things I want to mention in this particular plot. First, if you go to the gear box, the gear next to the plot properties, yes,
yep.
There's a magnification slider, so we can magnify the amount of deformation we're applying. So you have a much better sense for how it actually is deforming. So there's going to be a good amount of actual sort of shrinkage, but also if you look at the red end, the corner in the left, actually there's a lot of out of plane deformation, and actually that could be a bit of a problem. So one of the things you can do now is go back to like magnification 0. We have now a property for flatness. Yep, activate that. if you turn the part around, so this is a part where like you have two mating surfaces now, right? So if you can select a face, now we can see how much out of plane deformation there is. And that's going to be very important for you to, if you have two mating parts that have to fit together, there's going to be a tolerance that you have to hit for this to be a functional part when these things have to be assembled. So we're trying to give you some ideas like how much out of plane warpage that's going to be and whether or not that's going to be acceptable for you. So it's really localized interpretation of data. So one of the warpage is a very important part of the injection molding simulation industry itself, but making sense of the data actually is in some cases not that trivial. So we're trying to recontextualize what the problem is we're trying to solve, and see if we can provide different ways to look at the same data and have even non-experts extract value out of this. And this is just beginning. There are other things we can think about, like around circularity of holes, position of bosses as a sort of requirement up front. So like I said, this is the first step. There's many things we can do in this particular area that based on this concept over here.
So I see these are the guided results. We also have just a results tab here. And here we get this overview or summary log. And this is, I showed this earlier, right? We can animate this. And I really love how it sort of calls out, this is the filling phase. Then we get the pack and cooling phase, and then we get to the final part shape. And even within this, right, we've got these sort of messages to say, hey, you might have problems here. These are something to look out for. This is going to exceed whatever. And so even just this is great. I love the animation that it sort of follows the part filling here in the machine. I think this is extremely useful, not only for your own understanding, but can be very useful even to explain to somebody else what's happening, when you get into discussions about your part. Besides that, I do see things, some of the standard ones that look more familiar to me, filling animations, where I can see just what is the pattern, right? How is this filling? Do I like the way that fills? Based on this, I might simply move one of my gate locations this way or the other way. Fill confidence. Again, we get back to sort of what was in the guided results here. Injection pressure. Again, I always want to make sure that it's not going to exceed the machine maximum. And a whole bunch of other results here. Let's see. Oh yeah, we get back to here to deflection. So the previous one we looked at was the warp tolerance, which again, I can kind of change that to see just highlight the important parts. But here I see the full sort of view of this with all of the colors. And one of the things that's a really nice feature as well is the inspect button. So I can, of course, say, well, what happens here? And I can click other areas too if I wish. And then those will actually move as I move my part around as well. But this is kind of, if I have specific questions on an area, I can get sort of an exact value right there.
I think another thing actually I was going to point out in terms of the time to reach ejection temperature. That I think is a very useful result. If you rotate your part, because I saw this earlier when we built up this demo. On the bottom left, we do see an area that's red, and actually that's an area that is really, really thick. And one of the problems here we have is that this thick area is going to take a long time to cool down, and that's going to dictate your almost your entire cycle time. So as a designer, you may not actually not have been aware of it, but this is actually an area that to make your process more efficient, to reduce the cost per part, taking those making the area thinner will make it take a lot less time to cool down and to to reduce your cycle time and reduce your cost. So those are the insights actually you can provide a designer, or as a designer, you can get an understanding what you can do to improve the efficiency of the model. So these are like pretty good guides, I would say, for you to look at.
Yeah, I like that. I mean, here we're 23, our peak value is 26. I mean, even the ones that are, not quite, more in the mid-range, I mean, that's a 10-second difference between sort of the higher other areas and the thick sections. I mean, if I can save 10 seconds off my cycle, that's money. Exactly. So that's pretty big. So very cool. I love this. I love that it's a bit more guided. I love the way the results display in this, and yeah, just some really great tools here.
Yeah. So you will see some traditional things in this technology preview that are going to be recognizable for people who use, let's say, Advisor and Insight in the past, or you maybe have consumed some result reports created by other experts. But we also have like a way to run the software without actually you needing to be all that super familiar with the injection molding process, or even simulation itself. So, and you can get insights that are helpful, as well as make modifications to it, or like address some of the things that before involving an expert, before you send it over to a tool maker for analysis, or for making the part. So we're trying to reinvent some of the things we've been doing for a long time. We've built experience in what are sort of the barriers, where are people struggling over the years, and we've taken a step back and see what can we do to improve on that, rather than just make it a straight re-implementation of what we've done for a long time. So with that said, I think we are, ready to take some answers. Questions and answers. So even if you want to talk to us outside of this, you have our email addresses below. So thank you for your attention.